Hopefully most folks have had a chance to at least try to run the serial example. I had some good questions during the break, so I just wanted to give a few more bits of information about the example, and especially running it on theta, which is a little bit more complicated than maybe a lot of MPI clusters or clusters you may have run on before. Someone asked, can I run this interactively? And yes, that's a good question. That's another way. So my example, the slide shows you how you can submit a script to the job queue, and it'll get executed, whenever that job gets scheduled to run. But if you, instead of using a job script, if you want to do dash capital I as part of your qsub command, that'll actually wait and until you get an interactive session on the machine. Then you can just run commands directly. But one thing you'll notice, much like this output up here is from an interactive job. And so what happens is you get your user session gets placed on a node called data mom and then a number. And so this node is where you're supposed to run your jobs. But again, you can't run the stencil binary directly. You'll get an error that says, oh, this is built for a different architecture. Make sure you're in the right place. And that's because, again, the theta mom nodes are not the KNLs that are actually the compute nodes of theta. So what you actually have to do, and I know we talked about MPI run, MPI exec earlier, but again, on a Cray machine, typically what happens is you have to run their job launch command, which in this case on theta is AP run or app run. And then if you give it your stencil binary and your input arguments, then you'll get to see the output interactively run on the theta node that was allocated to your job. And so that's an example of running on theta interactively. Again, hopefully folks are somewhat familiar with that at this point and are able to run. Let me see, another question. So someone said, oh, I tried to make, and I had got a permission denied error when I tried to build the binary. Just, again, make sure you copy the files, copy the examples to your home directory or to your project directory. You won't have permission to modify the examples directory unless you're one of the instructors who's part of the right Unix group there. So any other questions about the serial example so far? Otherwise, we'll start going through how to do the first parallel version in our tutorial. Okay. Okay. So we have our n by n square mesh that in the serial example is going to be calculated iteratively, just one mesh point at a time by the single process in the application. In the parallel version, we're going to decompose this mesh into, in our case, we're dealing with a regular mesh and a very simple example. We're going to decompose it into equal-sized pieces, work pieces. So in this illustration here, we've taken our mesh and divided it into nine pieces of work. Three in the x direction and 3 in the y direction. Theoretically, it should all be the same size, though that might actually be the case in that picture. This one's a little bit more clear. So this is kind of your really basic parallel algorithm setup, is decomposing your domain into pieces so that when you're running more than one process, they can all kind of operate on their individual parts of the mesh independently, and then they'll use MPI to communicate when necessary for the purposes of the algorithm. So again, we have n, which is the size of the edge in the global domain. So n is, again, the input on the command line was 1,000 in my example. And then we have px and py, which is the number of processes in the x and y dimension that we're going to be using to do the computation in our parallel example. And again, for simplicity's sake, we want n modulo, we want n to be evenly divisible by px and py. We're not going to be dealing with partial, allocation of mesh points to processes. Every process is going to get an equal number of mesh points that they're responsible for. So just when I'll show the command line input examples again, we'll see that everything needs to divide equally nicely, or else the program will actually abort and tell you try again with better parameters. So in the domain decomposition, so each process is going to start, and they're going to need to figure out, where am I? Where in the global mesh am I supposed to be working? Basically offset from the start. Who are my neighbors? Which ranks an MPI term? Who are my neighbors that I'm going to be communicating with? And then another thing we do for this example is we use for boundaries. So for processes that are on, say the left edge or the bottom edge or the top edge, there is no neighbor in that direction. So in our example, we're going to be using a special value in MPI called MPI proc null, which is a valid input parameter to a rank argument in a call, but it's just to indicate that actually I'm not going to be doing communication in this direction, so MPI knows that that's essentially, when you're communicating with proc null, that's essentially a no-op. But it's useful shorthand when doing these types of decompositions. So necessary data transfers. So we have a fancy animated slide here. Again, if imagine I'm the red plus there, so I'm doing the neighbor count. Sorry, I'm doing the calculation for the updated value of the point in the middle of the plus. So I need to get the value of heat in the north, south, east, and west directions. In this case, I have all that data locally. I should have all that data locally because this patch here represents my local data. But what if I'm calculating the value of the heat here in the mesh? Then I don't have the data to my north. So this is where I'm going to have to communicate with the neighbor who does hold the value of that data in the mesh. And so yeah, that's what that orange ball is indicating is, oh, I don't have the data, I need to get it. And so previously we had the global data structure in the serial example was all 1,000 by 1,000. In the local process, now each process is going to have a local patch of the global array, like I said. In this case, Bx and By are the sizes of the local array. And the local patch, in addition to the data that we're responsible for, the data that we're going to be calculating the updated values for, we also are going to allocate in yellow here what we call a halo around the patch. And so the actual array allocation, the actual malloc we do in the program is going to be using these dimensions instead of just Bx, By to allocate the local memory. And you can find this in the alloc buffs function if you're looking at the example code. And so then for our data transfers, we're going to be, after each iteration of the calculation, we're going to be exchanging data in this fashion. So we've got, our left edge of, so this is what's happening for this particular patch. But you can imagine this happening for all of the different points in the computation. So this we'll go back here and show it again. So the green data here is my border data, and I'm going to be communicating this to my left, right, up, down neighbors, and my neighbors are going to be communicating their border data to me, which I will then store in this halo region. And so that's what this illustration is showing here. So the data from this process in the middle is going into the halo region of this process to the left, and the data from the process to the left is going into my halo region here. And so then I have all the necessary information I need to do the 5-point stencil for all the points in my, along the border of my, my patch of memory. So we'll dive into this code and try and show, again, how we took the serial version and turned it into a parallel one. And we can also try and execute it. I added one image here showing, so this is, like in the serial example, I had an instance where this is, 1,000 iterations with the given inputs, the 1,000, so the third argument is iteration. So if I were to put 1,000, 1,000, 1,000, I'd get the image on the right, or sorry, the image on the bottom. And then in the parallel version, it's the same 1,000 iterations, but you can see these kind of horizontal and vertical lines. So these are actually representing where the data has been partitioned and then allocated to, in this case, a 16 process calculation. So we're doing essentially the exact same work, but we're spreading it out among 16 processes for in each the x and y dimensions, and then that gets aggregated together again when doing this image generation. So you can see the answer is still the same, and hopefully it's gone faster in this case, and maybe we'll see that when we execute this interactively or through the job submission scripts. So why don't I go down to the terminal again, and we'll look at the non-blocking point-to-point version. So we're skipping over the blocking point-to-point version. We're going to non-blocking because, as Rajiv talked about earlier in the session, in general, you want to avoid blocking operations because of potential unintended synchronization issues. So we're going to look at the non-blocking point-to-point version. And so first thing we'll see here, one is that in addition to the size of the grid, the heat value, and the number of iterations, we're also going to give it the size of the number of partitions in the x and y direction. So you saw that on my command line earlier, but we'll kind of cover that here. So the first thing you'll notice different, we're using MPI. We're calling MPI init. We're calling MPI com rank and com size on the built-in MPI com world communicator. Hopefully folks are familiar with that. That becomes usable after calling MPI init. We're going to do, again, our setup function has got a little more complicated here because we're going to be checking the additional command line arguments, the size of the partitions in the x and y direction. Let's see. So this is, right, so we're starting to see some of the ways we're using our rank to determine our position in the two-dimensional global array. So again, if I'm running this with 4 processes or 16 processes, I can identify my process in the world of the application, in MPI com world, by using MPI com rank. And then I can use that rank to kind of differentiate myself from the other processes so that I can know, oh, I'm process 0, I'm going to start at the very upper left portion of the array. If I'm process 1, maybe I'm one offset 1 partition to the right. So that's how typically in MPI we're going to be identifying what work we're supposed to be doing by using the size of the communicator and your rank within it as a process. So we have a neighbor calculation here. I'm not going to go too in detail of this, but basically we're going to be determining, okay, what's the process to my north? What's the process to the south, west, east? If that process, if actually there's no process in that direction, I'm going to be identifying my north neighbor as MPI proc null, for example. So again, that's telling MPI that there's no actual work to do in that case, but it kind of simplifies the way we use MPI later, where we can just call MPI send or MPI receive and without having to put a bunch of branches in the main loop regarding whether or not there's actually data there. Right, we're calculating the size of our local block based on the size of the global domain and the number of partitions. We've got our offset, which is calculated using our rank and the size of the block. There's a commented out print line here that actually prints all this information for you if you want to see it in action. And then it looks kind of similar to before. We initialize the sources of heat in the grid. We allocate the buffers, old and new, but now you see that instead of allocating a buffer of size n by n, we're only allocating a buffer of size of the block size. And so if in your simulation if you're trying to allocate the whole global buffer, it would be too big for main memory and it would be quite slow. This is an immediate illustration of how you save things by kind of dividing and conquering, right? So you only have to allocate enough memory for your local patch and the communication buffers. So again, you may need some additional buffer space to do communication. That's true in this example because we're going to be packing some of the data before we actually send it, as opposed or receiving the data into a temporary buffer and unpacking it into the array before we do the computation. Okay, so that's a very fast walkthrough of the changes to decompose the domain into individual work pieces of the processes in a parallel execution. Any questions? Okay. So now we dive into our iterations, our main loop here, where we're calculating the value of the grid points based on our neighbors, our old value plus any new energy that's been injected. We have some macros here that are being used to time the actual computation, and then now we've got the communication part. So this is all new in this version. So we have a data pack step. So if you remember our 2D array, so if we're doing communication, and again, assuming C, so you've allocated, you've done a malloc, you've got a continuous piece of address space, and in this case, it's allocated for MPI doubles or C doubles. We'll talk about data types a little bit later. But if you're communicating with your north and south neighbors, that data is essentially contiguous in memory. And so for MPI purposes, you can just tell MPI, here's my data. You can go ahead and send it to my north neighbor. Now for east and west, again, assuming C, if you've got X number, BX number of pieces of data, or BY pieces of data that you're going to need to send to your east and west neighbors. And these pieces of data are not contiguous in memory. And so you can't just tell MPI, I've got these doubles, send them. You're either going to have to pack them, or as we get into later, you're going to have to tell MPI how your data is laid out. But in this simple example, we're going to pack the data into temporary buffers and send it that way. So you can look at that function if you're curious about how that works. Then we're going to start all of our communication here all at the same time. So I'm going to send 4 different messages, one to my north, south, east, and west neighbors, and I'm going to receive messages from my neighbors. I'm going to complete or wait for all these communication operations to finish with this MPI wait all command. I'm going to do any necessary unpacking of data into my array, right? Because in this version, I'm using temporary buffers to do all my communication. I'll unpack the data into my actual array, and then I'll go ahead and do the update grid calculation, which is going to get the new values. And then swap, and then again, at the end here, we'll print out the image if we've reached the end of our iteration. So that's the very simple non-blocking version. Yeah, question.
Could you go to the wait all?
Yes.
So you mentioned it's better to have a lot of compute before we solve the data.
Yeah. So this version doesn't do any compute and communication overlap. There's still going to be a benefit in the wait all here, where instead of, if you were using blocking operations, you especially on the receive side, you risk all these operations progressing one by one, right? Because if you've called a receive, MPI doesn't know you're going to call a receive again, so it can only do the work for whatever operation you've informed MPI about. So the benefit of doing all this here is that you at least tell MPI about all the communication you're going to be doing, so that it knows about it. It knows where all the buffers are, and it can make progress on all of it at the same time. Whereas if you were using blocking operations, you risk serialization. But you're right, there is no overlap with the actual computation here. A better version of this would do that, where it would do some of the computation while the communication is happening in the background.
With this kind of stencil update, you need that data before you do the update. So there isn't a lot of room to overlap unless you make it more complex.
Yeah. Yeah, so at the risk of complexity, right, again, and for illustration purposes, our example ends up being quite simple, so yeah, but that's a good point. Yes?
So on a higher level, are you storing an expanded stencil for each of those domains instead of constructing stencil on the fly and then communicating the constructed stencil by reducing the operations? So there are two ways to approach this problem, right? Either you store more for each domain by expanding the stencils and knowing what the two neighbors are on each side are storing, or you can construct a stencil on each domain, on each part of the domain, and then you can communicate and reduce basically them.
I'm not sure I'm following the question. So,
yeah, I think I need to see the design.
Yeah, I'm not sure I'm seeing. So I mean, our example, and let me go back to, maybe if I have the slide up, we can talk about it a little easier. So in our case, we are allocating more memory than we are responsible for calculating, and that's so we can do these halo exchanges. So we don't actually update the values in the halos, but we need them to update the values in our local portion. So we do allocate a little bit more memory than we're actually responsible for, but that's a necessary cost of this algorithm. Yeah. You could, I mean, all processes could allocate the whole n by n grid. That would just be a waste of memory in that case, right? Because if they're only operating on a small piece of it, they would still need to communicate, because they still wouldn't have the values that other processes are calculating.
So just wondering, so each process is creating its own grid and halo, right? Independent of all the others. So you're writing the I send, I receive to say, later I'm going to need information so that we're all, because each one can't live independently. Right,
exactly. So and what's probably not clear, but when the update heat sources or whatever happens, so again, it's hard to do a simple example without getting complex quickly. But so where the heat sources are located in the grid, the processes actually calculate locally, because it's just a very kind of simple example. But then, once they start upgrading, or once they start updating their local piece of data, they can only do so, up until they need data from other processes, right? So for every iteration, they're going to have to communicate with other processes to get the portion of the data that they don't have. And so that's the idea here, is that once per iteration, we're going to need to calculate, or sorry, to communicate with our neighbors. Now we only need to communicate with the neighbors who have data that's relevant to us, right? So this process is not going to communicate with this process or this process or this one or this one. I think there are stencil algorithms that do that, but in the 5.1, that data is not relevant to the calculations being done here. And if I'm this process, I'm only going to communicate with this one and this one, and because they have the data that's relevant for my computation.
So there's a question in Slack.
Okay.
What does perf.com begin and perf.com end do?
Yeah. So those are macros that are doing performance measure. They're supposed to be measuring the performance of the program. And so basically what they're doing is so there's two different versions. In the serial version, it's doing clock get time, which is a Linux, Unix clock function. So it's saying what's the time right now, and then it in begin, and then at the end it says what time is it now, and then it does the delta, and it says this computation or this communication took this amount of time. In the MPI version, MPI nicely provides to you some functions to do this kind of time measurement. There's MPI W time, and so in the parallel version, it's calling MPI W time. In the begin, it's calling MPI W time in both of those macros, and it's again measuring. It'll take the delta of that and tell you how long it took for that actual part of the code to run. Yeah, go ahead.
Is the MPI topology similar to the Gardner topology limitations for that?
That's a very that's a big question. The answer is consult the documentation of your system in most cases. So the way processes get allocated on a node, the way they get allocated across nodes is often specific to the launcher. So that AP run in the instance of Theta. You can specify how many processes per node you want to launch. I'm doing everything on a single node, but if you were to launch on multiple nodes, you can say, I actually want 4 per node. You can give additional arguments to say, I want this process to kind of have this many cores allocated to it. So if you're doing, even if you're doing multi-threaded, you could allocate additional cores to a single process, so it has that additional compute available to it. Yeah, and then the topology of the nodes and how they're connected again is different from system to system, different from so there's different network connection topologies. They probably went over this a little bit in the interconnects track. There's Fat Tree, there's Dragonfly, there's things like that. So that's a very deep topic to get into. In general, hopefully the system you're running on has sensible defaults specified. So equal number of processes per node. You're binding processes to, hopefully a core or something like that, so they don't get interference. Where the operating system is scheduling, is preempting and moving processes around. But yeah, so MPI will try and get that information in a lot of cases, but it is a risk that if MPI is unaware of the topology, that then some communication can be more expensive than maybe you're expecting it to be. So yeah, that's a very tricky question and very, very important, especially at large scale, that you lay out your processes and your data in a way that kind of minimizes communication costs. Yeah.
So if we use DIMS and part, like the data types, to create a virtual topology, can we take advantage of, will MPI be able to optimize it according to the topology on the machine?
Hopefully. If it can't, you should talk to the MPI vendor for the system. So if you know about the MPI virtual topology functionality, there's a flag as part of that where you're creating your topology. And what MPI is supposed to do is that if you give the flag to say reorder my ranks, so you give an input communicator, you get back a topology aware communicator, and if you say go ahead and reorder the ranks, then what MPI is supposed to do is assign ranks to your processes such that given the communication values that you've given to MPI, it's supposed to minimize the costs of your communication. In practice, this often doesn't work. That the reordering actually doesn't do anything. So I think a lot of applications folks have taken to doing this themselves manually. But there have been publications, there have been advances in topology awareness in MPI. It's likely to be a little bit hit or miss if you're actually trying to use that on a production system. So try it out. If it doesn't work, ask the MPI folks if they can, if it should work. And if it doesn't, you may have to try and roll your own solution for that.
Yeah. So for this stencil case, would it be better if we use the collectives, broadcast, or various? So
in the Docker image, there are collective versions of the example. Better is again kind of dependent on potentially the system or the application, because in general, collectives are implemented underneath as sends and receives in many cases, and so this is this version is very very close to optimal in terms of what data is being sent and how it's being received. So collective might be cleaner from an implementation standpoint, where your code is more concise and expresses more in a smaller amount of code, and it's doing essentially the same thing. So collectives might be better from a code cleanliness point of view, but maybe not necessarily from a performance point of view.
Ken, which collectives are in the Docker version?
So we have a neighborhood collectives version, which is using a topology aware communicator, and there's an all-to-all W version, right? So does it create a communicator amongst your neighbors then? Sub-communicators amongst your neighbors? No. Oh, right, because all-to-all W, different processes contribute different amounts. So in some, for each all-to-all, some processes are contributing nothing where others are contributing something.
So the regular collectives are not well suited for this kind of nearest neighbor communication, because it's among a smaller group of processes and different groups just among each other. It's not among a bigger set. But there is something called neighborhood collectives in MPI 3, which we cover in some tutorials, but not today, where you can define this kind of a neighborhood and do a collective, in this Cartesian type of topology. So that would be one way of that.
Yeah. So is there a reason you define the yellow region in a different buffer than the interior? Because you can define everything in one array.
So yeah, we're getting a little ahead of ourselves. So in the non-blocking example, we take kind of a simple approach where the halo region, right, the communication buffers are all separate. And that's just, again, for illustration purposes, in the derived data type example, we're going to be doing communication directly from the AOLD or the AOLD buffer itself. We're going to be bypassing separate communication buffers. Yeah, in general, unless you determine that it's better to have separate communication buffers, you want to be communicating directly from where your data is stored to avoid that extra copy.
Do you have another?
No, I know that V is used for vector. You said W, and I was wondering what is W.
So I think W allows you to do not only variable amounts, but variable data types. Different data types, yeah. So it's okay. But in our example, we wouldn't. It's all the same data type, so we could probably all V might accomplish the same thing, yeah. Okay. We're doing okay on time. I can try. So that the example commands here, again, we're running in parallel now. But the examples here are still using a single node. You could easily modify the qsub command to allocate multiple nodes to your job and try and run it that way. And just as informational here, so I have examples. This is qsub for theta, which uses the ATPESC 2022 queue reservation queue. If you are going to run on Cooley, which I'm not really going to recommend, but if you are going to do that, then the name of the queue is, the name of the reservation is actually training. So there's a minor difference there. Again, if on Cray systems, so this is what the job submission script is going to do for you. But if you're running interactively, again, you have to do AP run. Now you specify the number of processes. In the serial example, it was just one. Now you can run up to whatever. A single node of theta has 64 cores. It's a KNL. I think 64, maybe a couple more. I forget exactly. We have our stencil example. So we have our domain size. Again, this is the global domain, the heat source value, the number of iterations, and then we have the partitions in the X and Y direction. And number of procs needs to equal X and Y, the X and Y dimensions multiplied together. So again, this is an example. This is a MPI run. So if you're running on local machine or if you're running on Cooley, we have 16 processes. We got our stencil binary. Again, the same input values from before, 1,000, 1,010. And then we've got, like I said, we've got 4 by 4. So we've got 4 partitions in the X direction, 4 partitions in the Y direction. And that's what generates this 16 square output image where these lines kind of indicate where the data is actually partitioned across processes. So, all right, we have till 12. So I have about a half an hour now to cover derived data types. And then we'll have some time to do hands-on actual modification of the code. So up until now, we've just kind of walked through the code. Now we're going to dive into how we might want to modify it to improve upon the non-blocking point-to-point version. So derived data types. So data types in MPI are a way of letting MPI, telling MPI, what your data is, and then MPI uses that information to serialize and deserialize, your data into messages, so if it's sending bytes over a network link or putting, data, moving data into shared memory or something like that, data types are a way of letting MPI know what your data is and how it should be treated. And the same goes for block devices in I/O. If you're using MPI I/O, MPI data types apply there as well. MPI provides several constructors to allow arbitrary data layouts. So beyond, in our example so far, we were saying, we were giving a predefined data type, MPI double, which translates to a C data type I'll show on the next slide. But it also defines these constructors to do arbitrary data layouts. You can use them recursively to make very complex data types that MPI can handle, no problem. Again, this is declarative specification, so it's what your data is, not how. So there's a lot of implementation optimization opportunities. A lot of it isn't really explored yet, but hopefully it'll be improving in the future. And choosing the right constructor, if you're using these data type constructors, is not always the simplest thing. So as I mentioned, MPI provides many predefined data types for the language types in the languages supported by MPI, C, C++, and Fortran. So if you're using C and you have doubles, you're going to want to use, those translate to this MPI predefined data type MPI double, as you saw in our example. And there's equivalents for C++ data types, Fortran integers here, which are different, or potentially different from C integers. So consult the documentation to understand how language types translate to MPI predefined data types. But then for more complex user-created data types, MPI provides these routines to represent them. So some of the basic ones here we'll cover in the next few slides. We've got contiguous data type, vectors, H vectors, which specify a stride between elements, indexed, which is a little bit more complex, which you're giving offsets from the start of a buffer, struct, which can allow for multiple different data types in a single user-defined data type, and then some other convenience data types like subarray. So we'll quickly go through a couple of examples here so we have enough time for the hands-on part. But this is an illustration of the type of thing you can do with MPI data type constructors. So in this case, we've got a buffer here starting at 0 going to 24. So imagine this is, I don't know what you would want to imagine this to be. But you've got green data and you've got blue data, and imagine these to be different data types. So maybe one is the green data is integers and the blue data is floating points. So I can define, I've got a contiguous data type of 2 integers, and then I want to define a vector of those contiguous integer data types. So the stride between each contiguous data type is then 2 of those types. Oops. So that's how a vector kind of works. On the right-hand side, we've got our floating point type is maybe we have an index. We want to define an index type that defines an offset from the start of the buffer where all of the relevant data is located, again, for communication purposes, because the goal at the end of this is to give this data type to MPI so it can use it to communicate that data in, say, a send and receive call or a collective or something like that. And then struct here, like I said, can actually have multiple, up till this point, up till vector and indexed, we're dealing with the same type basically underneath, a single type underneath, but if we were to say take a struct, which then has child types of vector and indexed, you can use the struct constructor to kind of define a single type which encompasses multiple data types. These things are kind of going up in complexity. So contig is the simplest, vector is still pretty simple, indexed is more complex, more expensive. You'll see that in the argument list for these constructors. There's more information you need to give to MPI to kind of define this data type, and more information means potentially more resources MPI needs to use to understand that type and deal with it later on. But anyway, contiguous, like I said, that's the simplest one. So you've got the API here defined at the top. You've got a number of elements contiguously defined in memory. You've got an MPI data type, old type. So if you're doing this, if you're creating your first data type, you're going to have to put in some predefined data type as old type. And then when this is done, you'll get out a new data type that then represents some contiguous amount of old type. So contiguous amount of integers or floats. Or in this case, maybe you've got some structs that you've defined, and then you make a contiguous data type encompassing those structs, something like that. So that's contiguous. We get more complex from there. Vector. Pay close attention to this because this is what we're going to be kind of using in our example in our hands-on. So again, vector is similar, where but there's some additional information here. So we've got a count, number of elements. I guess these are contiguously allocated, right? And then, right, oh, yeah, so you've got, sorry, the vector is the number of blocks in your vector. The block length, so the number of actual individual types. So if you look at this example, we would have a block length of 2, and we would have a count of 3. So we have three of these green blocks defined in our vector type. The old type, again, imagine this is integer just for simplicity's sake. And we have a stride here. So the stride determines how many elements from the beginning of the last one does the next one start. So the stride for this one would be in 3, I assume these are ints. So every 3 ints starts a new block of this vector. Hopefully that's mostly clear. And so again, you create that vector, you get out a new type in the last argument here, which then can be used, then could be used for communication. But there's another step that's needed. So in MPI, you need to call a special function called MPI type commit before it can be used in a communication function. So the caveat here is only the ones you're going to use in communication do you need to commit. If you're creating some multi-layered data type where you have a bunch of intermediate things that you're creating, and then you're kind of creating one last data type to then use in communication, you only need to commit that last one because that's the point at which MPI knows, okay, you're going to be using this type. Let me go and try and determine, how to best optimize this data type for communication purposes. So it might be an expensive call. Hopefully it's an expensive call because it's going to be, again, optimizing the library in order to handle that. When you no longer need a data type, you can free it so that MPI can give back the resources it used to store information about a data type. You can free a data type even if you've built, even if you've used it to define another data type underneath it. Only, that won't affect the data types you've used downstream from it. You can go ahead and free it, and that won't be a problem for your application. There's another function here that MPI provides called MPI type dupe that duplicates a data type. This is probably not going to be useful directly in an application, but if you're implementing a library with MPI and you need to create some sort of data type abstraction or something like that, MPI type dupe might be useful for you. So these are the simplest data types we look at in the tutorial. We've got slides that go over some more complex ones, but any questions about the kind of simple contiguous and vector constructors so far? Yeah.
So for the contiguous one, for the vector one, they have to be, all the blocks have to be evenly distributed, right?
Yeah, so the stride is a single value, so it's right. It's when we look at something like, well, H vectors, if you look at something like indexed, so if they weren't evenly distributed, then you'd want to use something like an indexed data type where instead of a single stride, you give an array of displacements. So, and that has to be, again, the size, that array has to be the size of count to represent the number of blocks in your data type. But yeah, so things, vector is quite simple and things can get more and more complex. But right, vector is all regularly spaced. Yeah.
Does the stride depend on whether it's row major or column major?
So I don't. So I think that's a good question. I'm not a Fortran expert.
You're the one creating the data type, so based on how the array is laid out, you need to take that into account to specify the stride.
Okay.
Yeah. So in our example, because we're using C, we're doing this in C, and we're using row major, I believe, right, notation. So then your columns are going to be the ones that are not contiguous in memory, and therefore you need to define those correctly in order to using vector in order to communicate them directly from the from memory. But yeah, I think if you were doing Fortran, it would be the opposite. So yeah, that's right. It's up to you basically. Yeah, you have to know how to define that based on how your data is laid out. Okay. All right, so again, we want to have time for the hands-on here. So H vector, so in the vector type, you define the stride in number of old type. With H vector, the stride is defined in bytes. So it's a little more flexible in that regard. So we have an example here. This would be a vector here on the bottom where the stride is in 3 old types. But if your stride is actually not in the size of old type, then you might want to consider using an H vector, which you can do the stride in number of bytes instead. So it's just a little bit more flexible when defining the stride. So it's still a regular stride. It's still regularly laid out data. It's just that the stride is defined in bytes instead of the size of old type or number of old type. Index blocked we talked about. So this is similar to vector, but instead of a regular stride, you have an array of displacements from the beginning of your buffer. Indexed is more flexible still. So instead of having, index block, each one of the blocks is regular size. Each block is, in this example, is 2. In indexed, each block can be different size. So that now we're defining an array of block lengths in addition to an array of displacements. So again, we're getting more and more complex here. We're giving more and more information to MPI. In general, that means MPI has to do more work and may or may not be able to optimize because, again, we're getting kind of more and more irregular here, and less regular things are harder to optimize for the library. And then struct here, again, like I said, you can, so now we have an array of block lengths, an array of displacements, we have an array of data types, array of old types. So instead of a single old type, now we have an array of old types. And again, this is the most general constructor and the most costly from an implementations perspective. And then another one here we highlight is a subarray. So this is a convenience function. So it's something that I think in the history of MPI, a lot of applications were doing these types of things kind of on their own. MPI provides kind of a convenience to define, say, if you have a 2-dimensional array, you can define a subarray here, maybe defined of this patch highlighted in blue. So we're not gonna touch this in the hands-on, but it's good to know about that MPI provides such functionality. So to summarize derived data types, a very quick introduction to derived data types. They're a sophisticated mechanism to describe any layout of data in memory, really. You know, they're quite powerful. And the hierarchical construction allows them to be just as complex as how your data is laid out. But beware that complex layouts require more complex data type constructions, and that's going to be, again, maybe not possible to optimize from an MPI library perspective, just depending on the complexity of your data. As far as the current state, like I said, it's not always the case that MPI is going to be able to optimize your communication for your data layout. In many cases, derived data types don't perform great in MPI libraries, but they have been improving in recent years. That's due to a variety of things, better code generation at the library level, increasing amount of hardware support for certain data types, particularly vectors, I think. But this is another example of a thing where if you're trying to use derived data types in your application and you think their performance isn't as good as it should be, complain to your MPI people, and hopefully they can help you find a way to make it go fast or fix any bugs that are existing in the code. But we would encourage you to not just stop using it, because that's a recipe for nothing to ever change. So try it out, complain if it doesn't work well, and hopefully we can make progress on making it work better. So now we're at the first hands-on where we're going to ask you to modify the code the stencil code that we've been looking at so far. So the idea is, right, we've got the basic version. We use non-blocking communication, great, but we're using manual packing and unpacking of data into temporary communication buffers. Let's try and use derived data types. So, and what we're going to be doing here is specifying the locations of the data instead of manually packing and unpacking. So ideally, what we want you to do is take the non-blocking point-to-point stencil.c code, open it up, remove the manual packing portions of that code, and instead create data types to describe where the data is located in your local memory and communicate directly to and from those buffers in your code. So I think we want to give, what, 15 minutes or so for people to try this before we move on. We can come back to it during lunch, and if folks want to keep iterating on it. 15 minutes is probably not enough time. Yeah, but at least for now, we'll kind of leave up this slide. Folks can take about 15 minutes. You can ask us questions. Also, the solution is in the derived data type directory in the examples. So if you do want to peek and see how it's done, the answer is always there. But just as a hint, we've got these those arrows here. So we're going to be communicating, our data. If you look at the pack function, you can kind of see the pack function will at least tell you, how to get the data that you're interested in, right? And so then you can kind of use that as a starting point to kind of engineer how to communicate. Instead of moving that data in a temporary buffer and sending it, you can then figure out, oh, this is where my data is. Why don't I maybe send directly from here? So for like I said, for the north and south regions, this data is already contiguous in memory. I think our solution actually creates an MPI type contiguous type for it. You can do that if you want. You don't necessarily have to. The one that's really important is these columns, these left and right neighbors, because these are not contiguous in memory. As I kind of hinted to before, you might be able to use a regular stride to access all of the data that you need to communicate to your neighbor. And so that would be where you probably want to spend the bulk of your focus, is defining the data type to send these columns to your left and right neighbors. So take some time, look at it, and then I don't know.
Yeah. Look at the syntax of MPI type vector online. Just
yes.
Parameter.
Right. If you're running on Theta, or if you have MPI installed, I don't know if the Docker container has the man pages also installed for you, but yeah. But you can just Google for MPI type vector, and that can help you.
I'm going to talk about the one-sided. This is the remote memory access part of MPI. Maybe one of the things to start with is, while MPI does have some higher level features, MPI really is designed to provide very low level control of data communication, data synchronization, and data movement. So a lot of what we'll be talking about will reflect looking at how memory is laid out and how we move it. And so some of the questions that have come up already about, for example, Fortran versus C and so forth. In MPI terms, MPI is looking at an underlying memory model. So understanding how the layout of memory maps to how, say, multidimensional arrays are represented in C or in Fortran or whatever you're working with, or how you're laying out your data structures is going to be important. Another piece of that, and again, this reflects some of the questions that have come up, is that both the strength and weakness of MPI is that it doesn't have any explicit support for distributed data structures. It has all of the things that you need to build whatever support you need for those distributed data structures. So that's the good news. The bad news is you have to do all of that. That's one of the things to remember. And what I'll be talking about in this section is another set of tools that help you build those operations on your distributed data structures. So the basic idea here in one-sided models or the remote memory access models is we want to separate out this issue of moving the data from synchronizing or understanding that I have moved the data. We've already talked a little bit about this in that example of the sort of unexpected synchronization and the impact on performance. And so the one-sided model allows you to specify what data you're going to move, and you can specify a whole bunch of different moves, and then say, now I want everything to be synchronized. And so if we look at this, if we start with sort of a typical MPI application, we've got processes. Each of the process has some memory that the process is using. What we might want to do is say, well, let's make some of that memory remotely accessible. So this already is a feature of MPI that allows you to say, there's a piece of memory that I want to be remotely accessible, which implies that the rest of it should not be remotely accessible, as opposed to all of my memory is accessible to other processes at their own whims. To start with, I can define all of this remotely accessible memory as it's remotely accessible. So I can think of it as global. In other words, I've got a way from any process to access that data. And the access may mean update it, it may mean read it, it may mean modify it. So another question that came up was about the halos and this need to have additional space. One-sided operations, at least in principle, can give you a way to directly, for example, add into data that's on a remote process, and we'll see that later. And so we can look at these sort of operations here, and I've got, let's see, I've got one operation here. This is a get. So this process says, I want some of this data. Here's a put, which says, I've got some data here. I want it to be over here. And I'll say that this one is, this is also maybe a get, but maybe it's a modify and then get. All right. Okay, and so it's another example of what's going on here. Let's contrast the send-receive model with the one-sided model. And so again, here I'm going to say I've got my processor, I've got memory, I have sort of implementation queues that are handling how I send and receive data. And in the two-sided, so for example, I might issue an iReceive or receive call that adds an element to this receive queue. And again, as we talked about a little earlier, if I haven't already received a request to send, it goes into a posted receive queue. Then maybe later, the other process, the one that's going to do a send, starts a send. That information goes into the MPI implementation. Once it matches, and even here, I've simplified things because I haven't included, for example, the request to send and the handshake. This might work with an eager one. There's a match, and eventually the data is directed into the target memory locations. In a one-sided case, so first of all, the receiving process doesn't do anything. The sending process tells the MPI implementation what it wants to send and where it's supposed to go. And all of that happens in that one call, that, as we'll see. And that allows an implementation, for example, to just move that data. There's less of the handshakes and so forth. Now, having said that, there is stuff you have to worry about. So it's nothing, of course, is as simple as it seems. Another advantage in using the one-sided is because it separates out the data transfers from the synchronization, you don't get these sorts of delays, again, like we saw at the beginning this morning, that are caused by the receiver and the sender waiting on each other to do their thing. And so, for example, if I do an actual send or I do an ISend but then have a wait all, that can't complete until there's not only is there a matching receive, but in fact, until the receive has finished, or at least finished on the sender side, the data has gotten out. Whereas in the one-sided, these things, I can start these things off and I can go off because defining the data motion doesn't include that synchronization. Okay, so we'll have to have that synchronization, but again, a lot of what we need to do to get performance is to eliminate from the code unnecessary synchronization that slows us down. So, and the one-sided gives us another way to do that. So as we look at the one-sided, what is it we need to know? Well, we need to know how to create or define that remotely accessible memory. We need to know how to initiate or manage those data transfers. We will need to know about the data synchronization. And then the last most painful piece of this is understanding the memory model. And as a foreshadowing of that, one of the things that's very difficult, and it's difficult in shared memory, and you would have seen, I wasn't here yesterday, so I don't know how much you covered it with the OpenMP model, but I'm sure you would have seen some of it. There's a lot of very tricky issues in shared memory in terms of understanding when an update performed by one thread or process is visible to another. And things that you assume are in fact not required by most of the languages and environments. And I said that a little this morning about the I/O systems. You know, you often have an assumption about, oh, when I'm done with that, that means that everybody can see the data. Well, it depends on exactly what's required. And why is that? It's because having that assurance that, you know, I've made a change here and it's visible there, that adds some synchronization. That adds a delay. That adds expense. And so the reason, for example, that shared memory systems have all of these weird things about when is the data visible and memory flushes and so forth is that if they didn't have those, they might be easier to program, but they'd also be slower. And so this is part of our trade-off. And as I said, MPI is a fairly low-level system. And so you get both the benefits and the disadvantages. The benefit is you can arrange things to be very efficient and fast and scalable. The disadvantage is you really have to watch what you're doing and be careful. Okay, so there are also a lot of functions. And in fact, the MPI-2 RMA was pretty simple. And we used to do this tutorial and do all of the functions. MPI-3, let's just say, made it much richer. And we're not going to cover all of the functions. But happy to talk about them during lunch or during the breaks if you have any specific interests or ideas or wondering, well, why don't they have one of those? Maybe we do. Anyway, so, okay, so the first thing to do is how do we create or indicate that memory is accessible, that it's part of this the object that we're going to allow other processes to access the memory. So one of the things to remember is the model that we have, the processes have memory, that memory is private to that process. And so you start like that. We are going to show some routines that allow you to designate some memory as visible to other processes. And we'll call that that remotely accessible memory the window. And just to keep things a little confusing, the collection of the processes that are sharing that, that's also a memory window. So I think partly because we wanted to think of those as providing this global collection of available memory. Once you've done that, then all the processes in that collection can perform those remote memory operations on that memory. As we'll see, the group of processes that involved is specified by, what do you think it's going to be specified by? How do we always specify groups of processes in MPI? A communicator, yeah. So it'll be a communicator. So we've got the same sort of flexibility that we have with the collective routines. We have other communications we have with libraries. We'll use a communicator to specify that group of processes. And we'll get back a new object, this MPI window, which contains information about that group of processes as well as what's going to be this remotely accessible memory. There are 4 models for creating this memory. In MPI 2, there was only 1. And we'll talk mostly about one of these. I'll say a little bit about 2 more, and we're just not going to talk about the last one because we don't have time. It's an interesting one. So the one which is preferred for the sorts of things that we're going to be talking about today is MPI Win Allocate. That one is going to give us a way to create a memory buffer, which is then shareable with other processes. Well, the reasons we do this is that, as always, that gives an implementation more freedom to pick memory that is good for this. Now, that's not always convenient, and so, in fact, the original version of the MPI 2 version of RMA only had one way to create this window object, and it was MPI 1 create, where instead of giving you back the memory, you gave it the memory. And so you know, maybe you malloced a big array. In Fortran, you had the array. Maybe you allocated that array. Maybe it came from someplace else. You would give it to the routine, and again, you would get back that window object that describes all of that. What if you need to do RMA operations, but you're doing, say, dynamic mesh refinement, and you don't know what the memory is to begin with? Well, that's what MPI Win Create Dynamic is. It creates a memory window to which you can add and remove memory later. There are trade-offs for this. That's why it's not the only version. But that was added pretty much explicitly to handle cases like that where the application is going to change the memory that it's using over time. The last one is, I think, really interesting, and which we were talking a little bit more about. Again, we don't really have the time. But it's going to take all of these ideas for remote memory operations and apply them to shared memory. But shared memory between processes instead of shared memory between threads. And that is the MPI Win Allocate Shared. That does not guarantee, for example, you can't take a machine with 20,000 nodes and say, I want to allocate shared memory across all 20,000 nodes and then do RMA operations. This is present to allow you to say, oh, I've got a node which has a couple of hundred cores. In the hardware, the memory is just shared by all those cores already. Why can't I use it in the shared memory model? That lets you do that. Right. Okay. So let's go into some of the details. Here is Win Allocate. And like with most MPI routines, even though it has a fair number of parameters, it's really pretty simple as you just go marching through them. So I've got a size. So remember, allocate is going to return me some memory. So how much memory do I want it to return? That's the size. There's a displacement unit. The displacement unit will be used to help me more conveniently access this data. So let me just sort of defer that because I want to put that in the context of those operations. Now there's an info. MPI info was also added in MPI 2, as a way to provide hints about how MPI object was going to be used that allows the MPI implementation to optimize things. So for example, I can say here that I guarantee that I'm not going to use this window in a certain way. The MPI implementation can go, oh good, I don't have to provision for that. I don't have to be looking for that. But that can also be MPI info null. In other words, I have no hints, or I don't want to think about it. There's that communicator. So we're going to have this communicator. The purpose of that communicator is twofold. One is to specify the number of processes. The other is this is a collective call over that communicator. And it basically has barrier semantics. There is the return pointer, and this is a C idiom. So that pointer is the address of a pointer. So you might think it should be void star star. But C has this little weird thing that if it's void star, it's an anonymous pointer, which means that you can put anything there that's a pointer and it will work. If you put void star star there, then it's a pointer to a void star, which would mean you would have to cast it. And so the idiom that's used not just here, but elsewhere in the MPI standard and in many C libraries is you just do void star when you need an anonymous pointer, even if it's an anonymous pointer to an anonymous pointer or a non-anonymous pointer. Okay? So in other words, if I have a pointer to double, let me call it a pointer, then I would pass address of a pointer there, even though that would look like a pointer to a pointer. It would match this. The compiler will say, this is idiom, I'm fine. Right? If we had put void star star there and I did ampersand a pointer, I would get a type error. Okay. And then the last output is the window object, which just like when you create a communicator and then you use that communicator in send and receive operations or in collective operations, we'll use that window object as the input to the RMA operations that we'll talk about. Okay. And so here's an example of when allocate. We do a sort of init, we do an allocate. I'm going to get 1,000 ints. I'm going to use a displacement unit of the size of int. Again, we'll see why that makes a lot of sense. Info null, like I said, infos could be null. Don't worry about it. This would be over com world. Get back that address of a pointer to int, and then also get back the window object. When I'm done, as with most MPI objects, you do MPI whatever it is free, you do MPI win free. And also, as is the style in MPI, you pass the address of it so that MPI can make it null so that it's you're less likely to then accidentally use it again. Create is fairly similar. The only real difference is that instead of it returning that address, you provide that address. And because you're providing it, the address appears first in the argument list, sort of like it would in a send. But otherwise, this is the same. And here, for example, I go ahead and I create this memory. I fill it in, then I pass it to MPI win create. If you're using older versions of Fortran, then this is easier to work with because older versions of Fortran make it harder to work with return pointers. Versions of Fortran after Fortran 2008 work fairly smoothly with the win allocate. Okay. And then we create dynamic. As I said, what if you don't know how much memory you're going to use? Well, in this case, you don't even pass it. You don't pass it any memory. You're not starting with anything. What you're doing is you're creating a window to which you are going to later attach and remove memory. So all you do is you provide it the info, the communicator, and you get back this window object. And when you get that back, there is no memory available yet. That will have to be added later. There's an MPI win attach, which attaches memory to a window, and detach. Win attach and detach can only be used with a window that comes back from MPI win create dynamic. Again, this is part of MPI trying to optimize for some different cases. Handling the reason we didn't start in MPI 2 with something this general is that this introduces additional costs. And so if you don't need that, you don't want those costs. All right. Okay, and then here, this is an example. You create the window. I could do an attach. Then I could work with it. We'll see how to work with it shortly. Then you detach it, free the memory, free the window. Okay. I'm going to, we want to let you go to lunch in a couple of minutes. So I'm going to do is just start talking about some of the data movement routines. We'll wait until after lunch to talk about synchronization and going into some of the details about this. So this is a summary of what's provided for the RMA operations. There's put, so it's a one-sided put to take data from one side. It's going to put it into another process's memory. There's a get, which just does the reverse. There's an accumulate, which is a remote update. So that allows me, for example, I can add data to a remote process. There's a get accumulate, which allows me to read the data, modify it, and update it. So I can read the data, get that returned, modify the data present. And then there are some special cases. There's a compare and swap and a fetch and op. So the fetch and op is like get accumulate, or it's a short form of get accumulate. Good, for example, say I have a remote counter that I want to update, and I want to do that atomically. I can do that very easily with fetch and op. Okay, so what do these look like? And again, they have fairly lengthy argument lists, but if you break them down, it's very simple. It's pretty obvious what they are. One of the reasons they're a little more complicated is that all of these routines, with the caveat on the compare and swap and fetch and op, allow you to use those MPI data types. So we can do these operations not just with contiguous data, but for example with strided data or even more general index data. But that then means that just specifying the data that I'm putting. So what do I have to do if I'm going to put the data? I have to specify where it's coming from, but now I also have to specify where it's going. So when I do a send and receive, I just specify, either the sender specifies where it's coming from and the receiver specifies where it's going. Now I have to do both. So in the put, that first row specifies the data that where it's coming from. So that's specifies the data in the local process. So I've got a pointer, a count, and a data type. Okay, where is it going? So rank. That's the rank in that communicator that we use to create the window. Okay, and then where? Okay, so a pointer on my process may not be a valid pointer on the remote process. So instead of using a pointer, which I can't even really figure out what it actually means there because that's some other person's process, what I use is a displacement from the beginning of that window, because that's easy to describe. So I wanted to put this data in the very first location in that memory that I said, you can use this memory. That's the exposed memory. The target displacement would be 0. Then there's a target count and data type that just, like in a receive, specifies the data type that's used, if it's non-contiguous, how it's laid out, and then finally the window object. Okay. Now, that target displacement, now I can talk about the displacement unit. So what does that target displacement mean if it's not 0? And so it refers to sort of number of elements of size displacement unit. So if I'm thinking of this is an array, I'm making a global array, and I want to access the 4th element of that array of integers, then I can use a target displacement of 4 if my displacement unit is size of int. Because then it says 4 sizes of integers. If I want to do byte displacements, then my displacement unit is 1, and I have to do all of that arithmetic. I may want to do that arithmetic, that gives me more generality. But if I'm, for example, working with a big array of doubles, if I make my displacement unit the size of a double, then I can just think of that target displacement as the offset in terms of the number of doubles from the very beginning of that memory. Okay, so let me just do, I'm going to do get and accumulate, and then we'll stop and do the others after lunch. Because get is basically the reverse of put. In this case, I want to specify where the data is going to be deposited, because I'm going to get data. So that's why there's not a const in front of the origin address. But then the same thing. I've got the rank, the displacement at the target process, the count, the data type in the window. So it looks just like put, except data moves in the other direction. And then the last one that I want to talk about before lunch, because these are the 3 that were in MPI 2, the original RMA, is this accumulate. And so this becomes a little more complicated because I'm going to take some data, I'm going to combine it with data at the target process according to an MPI operator. It's the same kind of op that I would use in MPI reduce or all reduce or scan. So I can, for example, sum. If I want to add some data to a remote process, I can do accumulate, specify the data I want to add, same way I will with the put, identify the target process, the process on which I want to make that change, the offset from the beginning of that exposed window, the data type, which, for example, could be strided, the operation that's going to be applied, and then the window. There are some restrictions. So the operation that's applied has to be one of the predefined operations, not a user-defined operation. If it was a user-defined operation, that would be great, because it would give you a way to execute your code on another process, because you could define that user-defined operation. That's a very powerful thing to do. It's also very complicated to implement, and we decided, the forum decided that that was asking too much of the implementations. So it still has to be just the predefined operations, but you have general data types. There's also a special operation, which is called MPI replace, which basically makes this accumulate look like a put. So why is that there? We'll talk about it after lunch. Right. Okay? Any questions? Okay, we will see you after. Oh, yes.
Maybe if you could quickly skip back to slide 90.
Let's see. I'm sorry, which?
90.
90.
Yeah. So here the comment says that collectively create remote accessible memory in a window. So I was just wondering, because we allocate 1,000 times the size of an integer, right? Does it allocate 1,000 times the size of an integer on each?
Yes. Yeah. So this is going to return memory on that process. And so in this case, each process is asking for 1,000 ints. If you wanted to create a window where everybody could access the data, but the data was only on one process, then you would use a different value here. You basically use 1,000 size of int on that one process and 0 everywhere else. It doesn't have to be the same value. Very good question. Okay, yes?
So for the get put operations, in what situation would your target count and or data type be different than your target count and or data type?
Wait. So say it again. I have to make sure.
So basically, like if I have like 20 doubles, in what situation would I have 20 doubles on the origin and want to put some?
Say you have 20 contiguous doubles on the origin, but you're transposing them on the target.